Right, so good morning. Welcome you to the talk today. I hope everyone had a great night yesterday. I had one too, and I will still try. I hope you will enjoy the talk as much as you enjoyed the wine cellar visit. If I actually knew that there will be that fantastic evening just before my speech, I would probably never agree to be recorded and put somewhere on the web. So this is the disclaimer for those who are watching this much later somewhere on the web, that to understand that. Yeah. Can you actually hear me? Does it work? All right. Is this better? Yeah, all right. Yeah, it's, yeah. So, all right. So, let's just go on. So, when I actually agreed to give a keynote speech, I wasn't completely clear exactly what I will be talking about. So, I was a little bit thinking about what the keynote speech should be. So, I think this is just kind of my thought what the good keynote speech should have, all these components. So I would like that you learn something new here, and maybe you get some inspiration for your future research. I'm not sure about the entertaining part that much, but I'll try. I would like just to ask you, can anybody raise a hand who actually understands how speech decoder works or has done some work in speech decoder design? Okay, great. So, so I will actually go. Originally, I thought it will be just some historical overview of some dry facts, like what happened, and then kind of when I put the foils together, it turned out more to be kind of like more like a tutorial about the basics of the decoder. So maybe for those of you who have been using speech recognition as a black box and sometimes wonders what's actually happening inside, this might be a good talk for you. So let me start, okay, this way, right? So let me start with a quote. I won't reveal the name of the person who said this, but that was back in 2000 in a sunny Orlando, and there was a late afternoon session, and a bunch of people were thinking about, let's go to the beach and enjoy the sun. And I said, no, there is a search session. And they told me, like, why would you want to go to search session? It's like the search has been solved. And that was about the time when then a large research lab, which is no longer a large research lab, came up with this great idea of finite state transducer and everything in the world can be expressed as a finite state transducer. So we just put it together and we don't care anymore, and everything is done for us by the finite state transducer toolkit. 8 years later, yeah, we are still people working on the search, on writing decoders, because it hasn't been solved. And let's see why it hasn't been solved. So let's go back to the history a little bit. So the dark ages of the speech recognition, I guess, date back to like 1970, or even before that. But in 1970s, the first, basically the statistical approach kind of dates back to these days. And those days, most of you haven't been born yet, so you probably don't remember how it was working on mainframes. So what you could do, you could play with digits and like a timid database, and you do some phoneme recognition or a few isolated words, and there was no notion of real-time recognition on mainframe, and but the work was done and the foundation was built. In early 90s, what big change happened in hardware? Suddenly we were getting PCs, relatively affordable platforms, 386s, 486s, little Pentiums, And those days, I don't remember exactly the year, but like you would be able to actually get first commercial speech recognition running on a personal computer using still special hardware. For example, IBM isolated system with 5,000 words vocabulary required rather expensive so-called Martin card, which combined DSP and some acceleration to do most of the work on that card and using the PC to basically run the search. And was very expensive and somehow worked. But very soon in mid-90s, when Pentiums arrived, I think the main big advantage of Pentium was that the floating point coprocessor was actually merged with the processor. So suddenly floating point operations became much more cheaper. And so people could start really focusing on like just the algorithm rather than figuring out how to do everything in integer and all the stuff around. So also the RAM became much more abundant, much more cheaper. And that's the time when you start seeing actually switching to continuous recognizers, 64,000 words vocabulary. That was particularly for English. Later on, for other languages, you needed much bigger ones. At the same time, also, what happened with in the hardware world was that the appearance of embedded platforms, which kind of lag behind in the hardware power. So basically, you had to kind of go back to the old days and try to use the techniques which were limited to the limited hardware before, and kind of became a cycle. So then we are moving to the 21st century, and suddenly we have huge amounts of RAM, 64-bit processors, multi-cores. So suddenly we have, also at the same time with the advance of internet, suddenly you have huge amounts of training data. So suddenly people were able to train on thousands of hours of recorded audio, which also which had a huge impact on the quality of the acoustic model you are dealing with. You could get text corpora, which with gigabytes or terabytes of words, so you can train language models. It's hundreds of millions engrams. So suddenly you get, and people started exploring other languages, inflected languages, with much larger vocabularies. So any of that would be impossible with these huge advancements of the hardware power. At the same time, the embedded platforms kind of move along, so they evolved, but there's always like few years like behind. So people working on embedded had to basically like they had this goal of like, yeah, we would like to do something what the people on the server can do, but we have all these limitations. Another interesting point I would like to make here about the hardware, especially in several recent few years, the appearance of graphic cards, which originally were designed for playing games, but people realized there is so much computing power, maybe we could use it for something else. So some companies like NVIDIA came with a CUDA toolkit, which was a software which would allow you actually treat it in some standardized interface. So it significantly improved the efficiency of the programming or make it much easier. More recently, there is an open standard, OpenCL, which is similar, basically same programming model as CUDA. And these are so-called many-core platforms, which is a really interesting platform, but requires many of the implementation of speech recognition algorithms, basically rethinking of the basic design, because of the parallel programming is significantly different from programming of serial or single CPU. So let's. So just a few notes about since I spent many years of optimizing algorithms for embedded platforms. So just a list of few things you had to deal with if you wanted to take an algorithm which would run nicely on a server, and what you had to deal with. So Of course, the memory was significantly smaller always. And not only that, common thing on an embedded platform is that you have a RAM or ROM or several different types of memories. So it's not the classic von Neumann architecture that you have one big block memory. You have all kinds of these memories with different speeds. And even the fastest one can be rather slow. The main problem was the cache. If there was any cache at all, it would be much slower, and virtual memory management was rather limited and slow. Usually floating point unit wasn't there at all. So all these things actually would mean that there was lots of much bigger effort you had to do to actually get a good, decent recognizer. But things are catching up. So if, for example, I guess he's familiar with the Android platform, which is becoming very popular. It's more like the mobile application. So you have a phone which fits into your pocket and can easily run 60,000 or more, even larger vocabularies. And do other things like synthesis and maybe in translation at the same time, which is really amazing, I think. So, so just a few notes about like what do you do if you want to port some complex algorithms. So there are like several different ways you can approach this. Like usually things would be just scaled down. You would use much smaller vocabulary. Scale down the acoustic model. Instead of several thousand Gaussians, you would use only like 10 or 20,000 Gaussians. And you would spend lots of time tuning the algorithm for the specific platform, for the specific speed of the memory. And many times what we had to do, basically, we had to rethink the algorithm. Can we, if we have a given algorithm, can we find some similar algorithm which is much faster? Maybe with some approximations we can sacrifice few percentage here or there, but we get a much higher throughput. So, let's go now and let's look a little bit under the hood exactly what the decoder does. So there will be few faults now actually like talking about the basics of the decoder design. So those of you who know decoder like this probably will be well known, but basically what we are dealing with, we have a huge HMM network which composes all the components which basically is the language model pronunciation dictionary, and the acoustic model, which models the parts of the phone in various ways. The three main components of the decoder is the front end, which extracts the features. The features are then modeled by some observation model. 99% of decoders today use mixtures of Gaussians. Yeah, there are others. There are lots of research in like using neural networks or some other source of densities, but we don't really care about it today because we will focus on the search. So, if actually we just wanted to get from the decoder the best path, life would be much easier, but that's not what the application designer are satisfied. Usually they want something more. They want lattices because they want to have multiple hypotheses for many reasons. For NLP processing, you can generate n-best, and you can offer alternative hypotheses on the API on the user interface. One thing which is very important is to have a good confidence measure. Make sure that what you are showing is actually it's actually correctly recognized, which is very important for many applications. Sometimes you want to do things like adaptation, so you actually need to do state alignment and so on. So the decoder actually, because of these requirements, the decoder gets much more complicated. So here is the famous formula, which you probably have seen before, I think on Tuesday morning in the first talk, that formula was shown again. So yeah, so this is the math behind the recognizer. you are trying to find the best path which will maximize the probability that you have seen that word sequence given the observation, which is the series of feature vectors extracted by the front end. You can rewrite it by the Bayes rule. What I would just want to point out here that, well, that Bayes rule would actually, if you are not looking for the argmax, the proper Bayes rule applies that you have this denominator here, which of course for the max you don't need, but it's actually something which is very important if you want to have a good recognizer, somehow approximate this probability of the basically the prior probability of the observation, because that's actually the term which would give you a good confidence score, because then this would actually be the true probability that the recognizer gives you an occurrence with certain probability that that was actually the thing which was occurred. And most of the recognizers just do the first two terms, which basically is the acoustic model and the language model. Now that can be rewritten in the form below, which clearly shows you like how actually these are computed. So the first term is the observation model, which basically are the probability densities of each state of the HMM multiplied by the transition probabilities from one state to another state, which usually includes two parts: the HMM state probability, which kind of model the duration of each unit, and combines it with the contribution of the language model. So, so we know what we need to do. We need to find the path through the HMM, and why is it complicated? What are the challenges here? So there are tons of approaches how people implement the decoder. The reason is that there are many ways how you can do it. One of the things is like, how do you fit this HM network, also called search graph, into memory? Because it gets very large for large vocabulary, and especially for large language models. And how do you run it fast? What kind of pruning you use? And then you need lots of memory when you run the decoder to be able to track back the best path or the lattices and so on. And also, very important thing, how do you actually build the search space, the search graph, which is not trivial for a very large vocabulary. So let's just go very quickly through an example of like how this is done. So yeah, so first we start with the vocabulary. Let's say we have a word in our dictionary. We have a pronunciation dictionary which we translated the phoneme sequence. Sometimes you have also surrounding left context and right context, which you have to consider. You use decision tree to get HMM sequence. So this is just the basically linear sequence of states. And those numbers, if you can see it, I don't think you can see any numbers there, but those would be actually the indices to the observation model. So those are basically the Gaussian indices of the Gaussian mixtures you would then use during the search, which to compute the basically cost of each state given each time frame. So let's look at a trivial example. Let's say you have a name dialer for these. Well, you could have as much as four person if they have the right combination. So this is very simplified, right? Let's assume each word has only 3 states. Actually, I would have many more. Typically, you use at least 3 states for each phoneme. But so you build somehow this network, and then the search basically is done by expanding in the time into so-called trellis. So along the y-axis, you have the original states, and then you progress in time. And when you do this expansion, it's basically a trivial task of finding the best path through the graph. right? And it's done. That's why Viterbi is called time synchronous, because what you do, you start with at time 0 with the probability of the initial state, and each time you increment and you activate more states by basically computing the transition and the observation probability. And at every time, that's the blue line, and each time you have several states which have certain probability of getting there from the initial state. And you just keep going, right? And eventually you reach the final state, and you have the answer if you keep track of how did you get there, right? So, so what's important here to see on this picture is that the trivial, most easy way to write a decoder would be if we have the search space, the graph, create this big matrix, which would be states by time, and just basically remember in each state what was the previous state, right? So that's the most easy way to write the decoder. Works perfectly for few words, for digits, for small vocabulary. Won't work for large vocabulary because we would need a huge amount of memory. Right? So that's something we have to deal with. So first thing we deal with is typically you instantiate in memory only that current frame and the next frame, so you can compute the transition from one time to the next time. So the actual memory unit is like that blue line with plus the next one, and then you keep reusing that memory. And you usually don't keep all the states in memory active because, as for example, if you can see, these are like gray. It looks kind of black for me too, but as soon as probability of some states become lower, significantly lower than of any other states, you just prune them off and you don't expand them anymore, right? And the third important part is that how do you keep track of where you came from? If you keep track of every single state transition, you would need lots of memory. You can't do that. So what you can do is say, okay, I'm interested only in the word sequence for now. So I have to make sure I remember every time I reach the word end, I make a record of that. So something we call it traces. Some people call it tokens. It's basically the same thing, just like when you reach the word end. That's the red line, the red transition, which you have to make sure that put somewhere in memory that at certain time you came to that state from that word. And something called token passing by some people. It's basically all the same techniques are the same. They just use different names. Then when you finish one word, you propagate, instead of keep the track of the green path, you just propagate traceback information referring to your last trace. Those are like dashed lines. You just basically keep the pointer pointing what was the end of the last word before you enter the next word, right? So this shows you like what you need to keep in memory for those particle times. So when you reach the final state, you can basically recover the word ends. Right? So this is the standard technique how to deal with the amount of memory to keep track to find the best path. Of course, it doesn't give you word state alignment. So if you want to do something like adaptation, when you really want to know exactly the state sequence, you wouldn't do it in the first pass of the decoding. Usually you would do it later on when you actually have the best path or the lattice and have a special code which would do the state-based decoding on much smaller scale. Now, this would be the best path. What do you do if you need lattice recognition? So this wouldn't be enough because you see here you have merges from two different words. So you need to keep also memory at any state where you have two possible hypotheses merging. Again, you can limit it to the word ends, and then you can have this structure, if you could see it, basically is the information you need to generate later your the word level lattice. So this still looks simple relatively. So now, why there are so many different implementation. So this is kind of my view of if you try to somehow categorize different implementation of decoders. So this is definitely not complete, and it's just like, well, you know, my one way of viewing at it. So at the very high level, the older decoders can be either static or dynamic. Static basically means the popular way of having somehow compile the whole search graph together, and then just running simple decoder. So you can use like FST toolkit with a simple implementation of Viterbi. I will talk later and why this is, what are the limitations of this approach. The other way is basically to somehow build the network dynamically. As you do the search, you start building the network and propagate. So there were two major different approaches, asynchronous and synchronous. Again, now pretty much everything is based on the synchronous Viterbi decoder. I will mention a little bit about the asynchronous decoder, which was algorithmically very interesting, but much more complex. And the synchronous Viterbi, there are many different ways how you organize the way, how you build the network, and especially how you organize the token propagation, how you organize in memory storing of the traces. So we will talk more about that. So let's just go a little bit back into the very early days. You can imagine if you had a few words or maybe even a few hundred words, you could basically just somehow put everything together in one simple program and expand each word into a linear sequence of states. What was popular was word pair grammar, when for basically from you would have some probability of transition from one word to another, which was kind of a predecessor to more complex n-gram model. So this would be like a bigram without the backoff. Or you could write some very trivial small grammar, which would be possible to express as a finite state machine. These decoders usually didn't deal with the crossword articulation, which makes it much easier to construct the graph. So talking about the crossword modeling, just to illustrate the on an example, why is it complicated? So let's say this would be this would be our finite state machine, which would define our search space, and we expand it into the full HMM search graph. By this simple approach, by replacing each word by its states, sequence of states. This picture doesn't show the self loop, but otherwise it would be basically the full HMM. So you can imagine for each black dot there would be actually a self loop, and you have a full HMM. This is relatively easy to do because for each word you just replace it by the state sequence. You can still do articulation modeling, of course, inside the word, right? So the decision tree only asks for left and right inside the word, but there is no crossover between words. Now, this is actually, so there are a few things I want to show on this picture which are interesting. So this actually shows a graph which is already minimized by merging those states, a tail of the word 5. You can see you can actually merge those states together after first few arcs. You may wonder why I didn't merge it earlier, right after the F1. This is because the way how we actually build the network using finite state transducer, the arcs are labeled, but when you actually want to do the computation, you put you need to put some symbols on the states. So this is kind of one way we do it, by projecting the labels always to the states you are going to. That's the reason why actually have the same. You always have to have a same label going to the same state. But another important thing is here that because of this merging of the tail, what happens here? You have this merge point suddenly there, and you have to deal with that if you want to do lattice generation. So in this case, you would not only need to do traces of every point where the word ends. you also have to make sure that somehow you remember all the possible hypotheses which come to this particle internal state, because if you just propagate the best path, you would arrive to this state here, 5, and you wouldn't know, all the competing hypotheses coming here. So that's one thing which in early days, people would sometimes wouldn't use the minimization. Even the graph would get a little bit bigger. That would be the one particular reason, because it just makes complicated and it needs more memory to do the backtracking for lattices. The other interesting thing was that in the older processors, sometimes it was better to compute more, but in a linear sequences. So if you had longer linear sequences, you could do like graph factoring, which would work much better if you had longer sequences of states, because this minimization basically chops it and makes much smaller chunks of linear sequences. So now, just to show how much more complicated it gets when you do use left crossword context. So now you actually have to, after each word end, you need several arcs which would take care of the crossword context dependencies, and suddenly you have many shorter segments of states, and also you have many more points where the different paths can merge. So it gets much more complicated. Now you can imagine, if I don't show it here, but if you have a right crossword context, it gets much more complicated. So these are kind of just to illustrate the reasons why lots of decoders were limited to word internal context modeling, because it just gets much more complex. So I need to speed up a little bit. So just quickly to say a few things about like how the language model is done. So very popular method was just to write a grammar, use some kind of language which would express rules, and that you would have a compiler which would convert it to finite state machines. This was very popular. You could write it by hand. But it's still used. But the problem is that writing a good grammar is very difficult, especially if you want to get large coverage. And these systems don't respond well if there is something, if the user uses something out of the domain. Decoder will always give you some answer, but you don't know if it's correct or if it's like something completely different. So the tendency is actually to abandon rule-based grammar and use everything trainable using n-grams. So again, the n-grams are fully trainable models. They need lots of training data to work well, but if you actually can have that, the performance is much better if you have out-of-domain speech, because they usually tend to give you a proper answer, and then you can use some other layer of like NLP to find out actually that what you got is the correct thing. So one type of language model, which the n-gram, which became very popular, is based on is the Beckhoff language model. The reason why it is so popular is that it can be expressed as a finite state machine. So let's say this would be an example of some training data, and this would be the model you would get. This is a bigram language model. And so you can see each state represents as basically single word history from which you can go and estimate the probability of the word you actually have seen in the training data, or you do take the Beckhoff arc, which has some Beckhoff estimate of the unseen event. There is a little problem with this approach that this representation is actually incorrect sometimes, because you can produce the probability, let's say, of dog chases either as a seen event by taking dog and chases, or you can do the Beckhoff and you get also a probability, and it's not guaranteed that the back of probability actually will be lower. So there are some methods to deal with this problem, but usually this problem is ignored. Then there are many more complex language models. One example is a class-based language model. When you model, instead of words directly, you model classes and dependencies of classes. Either you decide manually or use some automated technique how to assign those classes. The original IBM class language model was basically modeling only dependency between the classes and then only the probability of the word inside the class. Now, these days, there are many experiments with much more complex dependencies. One of the problems here is that you can't really express this easily as a finite state machine. So you need some approach of lattice or an unbest rescoring. So now, if you have this language model which can be really large, how do you integrate with the search? Can you approach that? So before the finite state approach, finite state transducer approach, people try to use many different ways how to somehow dynamically build the search network using these using the language model and the acoustic model. There are kind of three main different ways how to do it. So basically, you start with the word loop, which was a popular approach to do word pair grammar. So you can recycle that idea, but you can duplicate that word loop for every state of the language model. So that's kind of one approach. More advanced approach is basically, instead of duplicating the word loop, you would just pick only those states of the word loop given specific language model history. Needs a little bit more memory management, but tends to be more efficient. And the other popular approach was basically multipass. Use the single unigram word loop to generate a lattice and best, and then rescore. Now, so from this kind of list, I don't have time to go through every single one. And it's not even complete, but these are all the possible decoders if anybody is interested to look into this. So everything was done like basically, how do we build a graph? And one technique which is worth mentioning here is the introductions of pronunciation prefix tree, or sometimes called lexical tree, that basically replacing the word loop instantiation by deterministic version of the word loop. Basically, you merge all the phonetic prefixes or state prefixes together. So single example here. So it's basically equivalent of determinizing the network. The problem with this is that once you do merge the prefixes, you don't know the identity of the word till you reach the leaf of the tree, right? So, and this is very important thing here, is that in order to actually run the search efficiently, you can't wait till you reach the end of the tree to find the word, because you need the language score sooner than that, because of the pruning. Because if you don't apply the language model early at the time, you would have explosion of the states, and you have too many active states to run. You could never run efficiently. So pretty much all of these techniques, even though they look very different, and there is always about how do you compute the LM look ahead. How do you solve the issue of finding, if you are a certain state of the graph, what's the best possible language model score you can reach from that state? So, okay. So basically, the approach here it was introduced. Attaches to each state of the tree list of possible words you can reach, and you can basically go through that list and find the best score. And that's a method you need to basically apply even if you use finite state transducers with on-the-fly composition or any of the newest dynamic decoders. This is the most critical part, and then I believe there is lots of research is still done, because there is many ways to do it, and it's not easy. Just a little bit about like the way how actually you handle the tree. So there are again two main different ways. You could just, for each language history, language model history, you could just make a new copy of the tree, or you could do something more fancier, like just instantiate the states specific for instantiate the state of the prefix tree which are active. So just as a single example, let's say you have a different language model histories, and you would just instantiate new tree for each of these histories, and you continue your search. Or you could have one tree, and you can attach list of histories and propagate the list of histories throughout the tree. So those are like basically kind of two approaches you can see. And this, I believe this approach is usually more efficient, because you can have a better memory management of propagating and these hypotheses, and recombination, faster recombination of those paths which become equivalent given the language model histories. So now it's so very little bit about the alternative. This is kind of more like a historical note. It's the asynchronous search is we used to have at IBM a very good experience with this approach many years ago, because it allowed us to do very memory efficient search on very large vocabulary. It's called asynchronous because it's as opposed to the Viterbi search, it's kind of it moves in time forward and backward, so it can revisit some of the paths you have extended, can go back, and so the advantage of that is that you can explore very complex language models. It's not limited to use models which can be expressed as a finite state machine. It's based on A-star search, and we used variant which was called envelope search. The basic idea of the A-star search, if you are finding a hypothesis which goes from beginning to the end time, and you are somewhere in the middle, you know the score of the path getting up to this point, and somehow you want to estimate the probability of the rest of the path. And where does that estimate come from? We don't know. But if you can guarantee that you have always upper bound of all possible paths going forward, the search is admissible and efficient. And the envelope search, basically what it does, it estimates this based on other paths going at the same time. I will show this on a picture right here. So let's say each of the black dots represents a certain word of a certain end of a certain word or certain hypothesis. So let's say you have two paths, PA and PB. Each of them have two words, and you want to expand it. And at that time, you can look and see, are there any paths which basically their path has some log likelihood which would be better than these, and you can prune based on the distance from this so-called envelope. And the nice thing about the search was that you could completely decouple the computation, the acoustic evaluation of the trellis for a particle word. So in the box, which would be called detailed match, where you would just basically compute everything based only on acoustics from time PA to some future time, and you will get a list of words which the acoustic scores, and you can just plug these to extend all the possible language model histories where it could fit, right? So it was very efficient because of this reason. The problem was that it was very. Yes, I have to skip this line because we are running out of time. It was a very efficient decoder, but it requires lots of heuristics and lots of parameters, and it was a very complex and not very robust. So basically, at some point, our stack-based decoder had several hundreds of parameters which needed some expert to tune, and when people came with Viterbi, which had like 1 or 2 parameters, there was a clear advantage. Just to note that it requires a fast match, which kind of limits the number of words you need to expand every time, which is an idea which is used by both asynchronous and synchronous decoders. In the asynchronous decoder, it would be easier to use it because it kind of runs seamlessly in the one direction. If you use fast match in Viterbi, there is a problem that the ideal fast match in Viterbi should run in the opposite direction to get you the proper estimations of the continuation, which is kind of hard to do if you want to do single pass decoding. So finally we get to the I hope I will still have a few minutes to say a few things here. So finally, all this work has been done, how to deal with the construction of the search space. Then the weighted finite state transducer idea came. And basically the main advantage is that all this graph building was formalized and put into a nice toolkit. Probably people are familiar with the OpenFST toolkit, which formulates everything, the language model, the pronunciation dictionary, and the decision tree, everything as a transducer. You put it in a black box and spits out the search network. Then writing a decoder is relatively easy because we have a decoder based on a finite state transducer, which has in the order of hundreds of lines of code and does all the work, including lattice generation. So why is it so efficient? Because you do determinization, minimization, kind of that determinization basically is does for you the prefix sharing, minimization does the suffix sharing, does more than that because it does global minimization, which can significantly reduce the graph further, which is really hard to do if you do some kind of dynamic expansion. What's really important here is the label pushing of the output labels. A simple example, so this will be a graph. Top is the graph, and you see that after the word "and," the last phone usually would depend on if you use right crossword context on the next phone. So those states are duplicated. The label pushing allows us to basically move the word label towards the beginning of the word, so you can nicely share all those tails. So word label pushing was really important, not only for sharing, natural sharing of tails because they have same phonetic sequence, but to reduce the graph size because of fan out in the right crossword modeling would really blow the size of the graph. Well, there are some. Why wasn't search solved by this? There are some limitations. If you have a really large LM, compiling the static graph first can be really time-consuming and memory-consuming, and you might end up with a graph which you just don't fit into memory at all. There are some situations when the determinization will not converge, or there are some situations, especially if you use some rule-based grammar, that the determinization actually causes a blowout of the search space, and you end up with huge graphs. Any kind of adaptation of the vocabulary, if you want to add a few more words, is difficult. And now there is lots of work on language modeling, which those models cannot really be expressed as a finite state machine. Just skip over this. Well, so one of the way how to deal with the size of the graph is a common technique called graph factoring. Basically, you replace linear sequences of states by a single arc, and you encode that information somewhere. So, like here, basically, that you replace by a single arc. This is a popular technique to reduce the size of the graph. just to show here that it works really well on word internal context modeling with no crossword. As soon as you apply the crossword modeling, those linear frequency states become much shorter and more fragmented, so you can see the effect of the factoring gets lower. And I don't show number for right context, but actually at some point with the right context modeling, the graph factoring is not necessarily a big advantage. Just a list of few other approaches how to alternatives to the standard OpenFST toolkit. There are some techniques developed to compile the static graph in an alternative way, or usually dealing with the construction of the transducer from the phones to the context-dependent unit, which is really tricky. I don't have really time to go through any more details. Popular important technique, on-the-fly composition. Instead of compiling the whole graph together, you just compile together all the decision tree information with the lexicon, with the pronunciation, and you apply the composition with the language model as you do the search, as you basically finding active states. The disadvantage is, of course, it's slower because there's some overhead and there's no global minimization. But it's actually quite questionable. Like sometimes, if you spend more work on the CPU and you have significantly smaller footprint of the information in memory you need to access, because of the cache misses, sometimes actually thing can be faster, even if you are using a much more complex algorithms. So, one of the problem with this, if you use just a standard on-the-fly composition, again, you are limited to language model which are representable as a finite state machine. Just some example of kind of what are talking about, like what are the graph size we get for certain size of language model. You see that the graphs can grow pretty fast. And this is not even approaching anywhere the types of language models we have available these days. So that's why you have to basically use some other technique than the finite state static compilation. So popular technique is lattice rescoring, having a small graph built and do lattice rescoring. Lattice generation is a very interesting topic. I thought I will go through a little bit, but I don't think I have time to actually go through that. So let me just say that the lattice rescoring is what really makes the decoder design much more complex, because it's really the hard part. How do you collect that information for the lattices to generate them efficiently, correctly, and without using too much memory? I think I have to skip this. So let me just say now a few more words about what a decoder, which is now our decoder we use at IBM for the dynamic search. This is a decoder which is part of the Attila training toolkit, which unfortunately is not publicly available, but it's we have partnership with some universities that they have been using it successfully, so we might be able to actually work with that. It's based on the idea of having a smaller word loop with only unigram language model, but that network is fully determinized and minimized using the word label pushing, and uses that method of propagating multiple tokens attached to each state of that network, and using a very efficient look ahead, which gives you several options there. So you can, for example, use smaller LM to compute the look ahead, but at the same time, as if you do the progress in the search, you can use much larger LM directly in the first pass. That gives you a big flexibility, and it can work with any type of language model, which is not limited to the one which can be expressed as a finite state machine. So just to summarize, basically, so two competing techniques right now we can see is based on either as having static search compiled with the language model of the size you can compile into a static graph and good high quality lattice generation, or a single pass dynamic decoder. It's many times the dynamic decoder approaches the speed of the static decoder on certain tasks, but there are still many tasks when the static decoder is much faster, especially if the search space gets fuzzy, if you have mismatch of the channel, if you have noisy conditions. So when basically the decoder is a little bit confused and has to explore more paths, the static decoder has an advantage. Also, the static decoder can have advantage in this scenario when you have one large multi-core machine with lots of memory. The static graph can be shared across multiple engines, and so then the advantage of the dynamic decoder of small footprint is not as obvious. Last few thoughts here, just to say a few things about more advanced techniques, which we use very efficiently in both embedded and our telephony applications, and used by other labs too. It's when you train the language model, you could consider something like extension of the class modeling by replacing certain predictable parts of the text by rules-based grammar, right? So if you're talking about some amount which needs to be paid, you could just say, I use a grammar here. So you can actually combine a language model with rule-based grammars, and you switch from one to each other inside the decoder. Has a big advantage of the amount of training data you need to collect, because you don't need to have every possible dollar amount in your language model training data. The other nice advantage is that you could actually have specific grammar. Imagine that would be like a vocabulary of phone contacts, and you could switch that grammar at runtime when you run the decoder, when you know who actually is using the system, and you can quickly customize the vocabulary this way. So this is a very popular technique. So this is kind of like, if you build a graph which should be based on the language model, and suddenly you encounter these embedded grammars, you kind of can go in and you go out. And what I would like to show here is like there will be this is not a problem which has been solved, but so this is kind of the inspiration for the future, where like things could get really nice if you somehow imagine that we would somehow run the search and you would enter the embedded grammar based on a certain history like AC. You do all the computation of the embedded grammar which has all the name list, and there is some other path which has different language model history. If you do a strictly finite state decoder, those both paths have to be fully expanded and fully explored and evaluated. Now, could you somehow reuse the matching of the top path, which the embedded grammar for names, for extension of the path below? Right, so you could significantly reduce the search time if you could basically factor the search this way. So there has been some work on that, how it's done. Usually it uses some approximations, but it's not a problem which would be fully solved. And I go to the last slide, and I think I'm just a few minutes behind. So this is just like, okay, so where do we go from now? And I think the main driving force here is really the new language models, much bigger language models, much more complex language models. How do the decoders keep up with that? It means like, where should we go? Is it more like finite state transducer, static search? Do we need more research in dynamic decoder? Some kind of factored search, which I showed here with the either asynchronous search or the embedded grammars. Maybe you can take some advantage of this asynchronous search. Yeah, that's basically.
Interesting talk. Questions? So how is it with suprasubatomic modeling? I mean, phraseology and emotions and so on.
I believe this is all done for this, based on the second pass. As far as I know, that nobody tried to include such information directly into the first pass decoding. It's usually this method works with lattices, so you just need decoder which has good lattices, which unfortunately wasn't. Yeah, I didn't have enough time to talk about that, but you can find some details in the paper.
Other questions?
What do you think is the main application of speech recognition, or of which the decoding part in, let's say future 10 years? Is it dictation? That everyone thought that dictation would be like the market.
That's Passer. That was 10 years ago, and the dictation clearly that didn't happen. I think the one of the most important factors is the company who do speech recognition. Somehow they need to make profit, right? So looking where the money is. So any kind of automation of any service which is labor intensive, that's probably the future is, right? So automation of call centers, replacing replacing the agents. That's one main focus right now. Other area is transcription of, say, medical records. That's a big area where the big potential is. Where the future goes, I wish I knew. It's hard to estimate, but I would see it's more of along the processing of data, large amounts of data, as a part of the trend of getting everything centralized and accessible, and heterogeneous processing of data. That's clearly something which I would say that.
You have here the last line is something completely new. So I don't know, it's not completely new, but I know it's not completely new. But what about, say, better integration with, say, things that are used in the text area, semantic analysis, phrase, semantic rows, syntactic analysis? Can you see, or do you see here something interesting?
I believe that's the way to go eventually. Just the problem is that the methods which work, which are used, the search space when you work directly on the lattices or NBEST, the space is much smaller. Right? So if you want to apply any of such technique directly in the first pass, it's just become untractable. But that's just a question of having enough power. So there is I didn't stress it out, but one main problem of lattice rescoring is like if the information is not in the lattice, you can't recover it. right? And we don't know, or we have some idea how much we lose from the lattice generation, but if we could use some really advanced technique like that directly in the first pass, maybe we could get much better performance, but we don't know because it's so hard to do. So, but a few years from now, with massive parallelization, maybe it's possible. So I definitely believe that that would be one way.
Okay. Next and last question, please.
One about future again. When do you expect disappearing of embedded platform?
Can't hear.
When do you expect disappearing of embedded platform?
I don't expect it. That there's some. When I think last year at the Interspeech, there was a panel discussion, and all the big players, Microsoft and Google, claim embedded platforms are useless. Everything will be done on the network. And I don't necessarily agree with that, because the embedded platforms are really becoming so powerful that I see in the next few years there will still be, and it's basically they're becoming so powerful that the difference between the embedded and the server will be smaller and smaller, right? So
actually, that was my question. I didn't ask the right question.
Okay, thank you very much once again. Thank you for listening.